zoom out here briefly. What we did at the end of the last class was, well, we said that if you just do a direct, explicit method, right? If we did it by explicit method, where we calculate the temperature profiles at a later time based exclusively on the temperatures at a prior time, what happens is that we end up with an instability, right? At r is equal to 1/2, our numerical approach is unstable. We'll never get an answer for larger values of the t that are desirable for us to be able to solve the problem, the longer length scales, while preserving resolution in the delta x, in the x scale. Okay. And so what happens is I showed to you guys that there's this method that's named after Crank and Nicholson. Conceptually, it's very simple. What you do is everything's the same, right? Except that when you are calculating the time step, when estimating the second derivative of the temperature with respect to position, you do the finite differencing and evaluate that both at the previous time n and the later time n plus 1 that you are actually interested in determining. Okay, so all of these temperatures at a later time index n plus 1, you actually don't know, right? So you want to solve for them, right? But what you do is that in the evaluating, in the estimation for the second derivative of temperature with respect to position, you go ahead and still incorporate in the temperatures that you still don't know yet that you are solving for, right, as part of the estimate, and you go off and take the average of that. Okay, and so what happens is that if we do a little bit of algebra, right, combining terms and moving things around, and then defining r to be alpha delta t over 2r squared,
Hey,
we end up.
Carlos.
Hello, hi.
On the equation above that you were just showing us, yeah, on the should it be where it says on the n plus 1 section, should it say tj plus 1? It says tj.
Oh yes,
to the n
yes,
plus
yes,
1. Okay, I
that's
shouldn't.
right. That's no. Wait a minute. Are you referring to this?
Where are you looking? No, go up one.
Where?
It's I don't know.
Here? That one. Yeah, that's a typo. That should be a plus 1.
Okay.
Yeah, that's one. That should be a typo. Yeah, that's a plus 1. That's right. Yeah, I missed that.
Okay.
Okay. Yeah. So what happens next is that you notice that at this juncture here, right? We did so this is what we had, right? We did some combination of terms. I think what happened is I had intended to copy that down, but instead I ended up what do you call it? Moving it over. I think this was the expression that used to be there. And let me see. I had wanted to copy that. Okay. And I think I lost it last time I did it. Oh no. What's going on here? Never mind. You get the idea, right? So what happens is that this expression here, right, is the we do a little bit of algebra combining terms, okay? And at the end of the last class, we went off and did our usual stability analysis approach, right, where we substituted, for a solution to be of a type of exponential e to the alpha k squared t exponential I k x, right? And we wrote that thing down in terms of a finite difference, not a finite difference, but in terms of a time increment multiplied by the time steps, and a position increment j times the position steps. Okay, and we went off and did the substitutions like what we had done earlier, and we came with the result, right? That this factor here, which is multiplying, which is the factor that's multiplying the previous time at a certain position, right, to calculate the temperature at a later time, right? So this is referred to as a growth factor, right? This was the expression we ended up with. And I showed you essentially that r, right, because 1 minus cosine k delta x is always, that's always less than 1. And so what happened is r is, of course, also positive. So this is a positive number. That's the same positive number. So if you subtract 1 by a positive number, and you add 1 to the same positive number, it's always less than 1. And so what happens is that the Crank-Nicholson, therefore, is stable for any choice of r. So whatever your time steps, whatever your your position steps, it's always stable, right? The solution does not blow up, okay? Well, cosine goes only from -1 to 1, right? So 1 minus, so this thing can either be 1 or -1. So 1 minus something that can only be between -1 and 1 cannot go negative. The highest value of a cosine is 1. So at most it's 0. Okay. Yeah, so where do you go next? So now the next step is, well, okay, so we got our scheme. We know it is stable for any value of r. Well, we actually now need to solve for the temperatures at the various nodes. So what happens is, you notice here, right? So we have several equations. We could write this equation down, right? We could write that equation down for any value, for every single value of j, okay? So remember, we start at n is equal to 0. Then we want to calculate the temperatures at every single j value, right? For n is equal to 1. So let's say if we start at n0 and we know all the temperatures because we know the temperatures at time 0. We know the temperatures at every value of j. And the j is basically we divide our bar, let's say, into 50 increments or 100 increments, right? So we have 50, 60, 100, or whatever number of values for the temperatures that we have discretized it at, right? And what happens is that we want to calculate then the temperatures at each one of these positions j, 0 to 50 or 0 to 100, however many divisions you made, right? And so notice what happens is that we have this equation. We can write that down for every single j value, for j0, j1, j2, j3, j4, j5. You keep writing them down. So the r is being less than 1/2. That is for the the explicit method that we did, right? In which we were estimating. So r is 1/2 limit is what happens is if you choose to use only this as your second derivative approximation. So the Crank-Nicolson, that's why it is so famous and so widely used, is because it is stable for any value of r. And in the Crank-Nicolson method, you're taking the average, right? That small difference makes the entire difference in numerical stability, amazingly. Okay? So what happens next is, so for every single value of j, we can write down one equation like this for every single value of j. So we go ahead and do that, right? So how many unknowns do we have? Well, we don't know tj at 0, we don't know tj at 1, tj at 2, and so forth. We don't know what they are, right? And so we have simultaneous equations, simultaneous unknowns, right? And these thankfully are linear equations, right? So you can write them out as a vector and a matrix, right? Ax plus b. You've learned how to do that in high school, right? And so what happens is you list down your unknowns, right, as a vector, and those are basically your temperatures. The temperature at 0, temperature at 1, temperature at 2, temperature at 3, and so forth, right? So you have a vector of temperatures, right, at the next n value, at n plus 1, because that's what you don't know, right? And then you look at this, is what are the coefficients that are multiplying each of these unknowns, right? In high school, this would be x, y, and z, right? And you'll have your coefficients that are multiplying x, y, and z. So, let me refresh your memory. So in high school, you might have something like x plus 3y is equal to 1, 2x plus y is equal to 6, let's say. Then you go off something like 1, 3, 2, 1, x, y is equal to 1, 6, right? That's what you used to do in high school, right? That's exactly what we are doing here, right? Except that instead of x and y, we have a lot of them. So we're referring to them in terms of tj, t0, t1, t2, t3, t4. And that's the vector there, right? And you notice that for every single one of these equations, there's actually only 3 terms. There's only tj, the one before it, and the one after it. So for example, if you're looking at t10, at j is 10, it will depend on temperature at 9 and the temperature at 11, but there's no dependence on the other temperatures further away in position. So that's good. It's a sparse matrix. That's what it calls. Meaning to say, if you write out your matrix, right, notice you'll have a 1 plus 2r down the diagonal, right? And then you'll have this negative r on the diagonal above the main diagonal, and a negative r for the coefficients that are below the main diagonal. Okay? Now, what happens next is, how about the right side of the equation? Now, on the right side of the equation, notice in high school before, well, that's usually a set of numbers that you know. You have to know this, otherwise you can't solve it, right? So let's see. Do we know it? Do we know what's on the right side? Yes, we do. This is just a calculation because you know the temperatures at a previous time n. Let's say when n is 0, you know what that is. So you know that value, you know this value, you know that value. You know what is r. You chose your delta t, you chose your delta x. You know the alpha of the material. And so this entire thing is just something to be calculated. Okay, you just calculate that out. All right. And so what happens is that, yes, so we go off and write these out, right? But there's something to remember here, because what happens is that when we are looking at the equation, at the very, very first equation, where j, right, corresponds to the leftmost boundary. Notice when j is at the leftmost boundary, what is this? You cannot go left more than one. Well, actually, it's not that you can't. It's just that you don't solve for it because the temperature at the leftmost boundary is usually given to you. So you know what this is when j corresponds to the leftmost boundary, right? I saw the question. Let me finish out here. So when j corresponds to the leftmost boundary, the temperature to the left of the leftmost boundary is the temperature that you know. So this ends up becoming a number when j is at the leftmost boundary. So there's a minus sign here. Well, you add it to the other side. Okay? Likewise, when j is at the rightmost boundary, well, you can't go one more beyond it and solve for that because it's actually something you know. That is the temperature at the rightmost boundary. So for the equation that corresponds to the last row of the matrix here and for the first of this matrix here, right? For the last row, this temperature here is actually added to the other side, to this side here. And likewise, for this corresponding to the first equation, for j at the leftmost position, this temperature here is added to the other side onto this side because that's a temperature you know. You're not solving for it. Okay? Now let me look at some questions here in the chat. Let me see. So the square matrix on the left is the coefficient matrix, and the center matrix is for variables, and those are. You don't call it so. So this, this should not be an equal sign there. That should be a multiply, right? So what happens is, let me see. There's no center matrix here, so we have this is our coefficient matrix. This is a vector of unknowns, right? This is our vector of unknowns, just like this is your coefficient matrix. That's your vector of unknowns, right? So usually in high school, I thought is AX or AV. I don't know what you guys did in high school. AV is equal to B, let's say, right? Right? So that's what you did in high school, right? And so what happens here, this is basically your vector of unknowns, right? And this side here, although this looks long, actually, that's just a number. You calculate all of that up. You just add up the terms that you know already. And so each one of this is just a direct calculation. And that's correspond to these numbers on your B, on the right side of the linear algebra question. Okay? And that's it. Okay? So what happens is that these kinds of problems, right? And you notice that everywhere it's 0, right? These kinds of problems appear a lot, like a lot in engineering calculations. So like, let's say if you're in mechanical engineering, especially, right? You will be solving a lot of force balances, torque balances, momentum balances, and so forth, in which what happens that a lot, you convert it to a matrix type calculation, and a lot of the elements of that matrix are going to be 0, okay? So, things like the dynamics of an entire car. Let's say you have like a lot, or like a bridge, for example, right? Every single element there, right, is basically a force balance, X, Y, and Z. And you will have some sort of a matrix like that with a lot of zeros, right? Likewise here, you might be wondering, so notice in this particular problem here, we're only doing discretizations only in one direction, x direction only. If let's say this was a real three-dimensional problem, like a real three-dimensional problems, where we are interested in the temperature, both in the x direction, in the y direction, in the z direction, well, just think about it. If we have a big object, right, and we chose to discretize x 100 steps, y in 100 steps, z in 100 steps, well, how many temperature nodes would you have? 100 to the third power, right? So that's 10 to the 6. That's 1,000,000 unknown temperatures. So that kind of problem happens. And so what happens is this matrices here becomes 1,000,000 by 1,000,000. That does not fit in most computers' memory. And so what happens is that there are specialized methods to deal with these kinds of linear algebra equations that are very big, but are mostly zeros. And these things are so widely used. I think it's good you guys see some of this. And so what happens is our particular coefficient matrix here, the A, is just as a diagonal above the main diagonal and another diagonal that's just below the main diagonal, right? What happens is that one of the methods you can solve these by is in SciPy. There's this method called solve banded. Okay, so this thing is used a lot. Okay, and so the way this thing works is, for example, right? If you have a banded matrix like this, you see this is the main diagonal. And then you have a diagonal above, two diagonals above, and a diagonal below, right? What you do is you create another matrix that incorporates only the bands, the diagonal bands, right? So you have -1, -1, -1, -1, -1, -1. Then the next band, 2, 2, 2, 2. Well, 2, 2, 2, 2. You notice that if you were to draw a diagonal right there, there'll be an element that lies outside, right? And so it's showing there as an asterisk. What happened is basically this solver just ignores whatever those numbers are in those asterisks there. They're meaningless, right? They're not part of the problem. And then down here in the lower diagonal, right, you have the 1, 1, 1, 1, 1, 1. And then the last value here is, again, it's an asterisk. This is just ignored. Whatever number you put in there, it doesn't matter. Okay? And then what happens is that when it comes time, so you enter your matrix like this in terms of the diagonals, right? And the next thing you do is you create a matrix with just the diagonal elements, right? And that is your matrix with just the diagonal elements. And then you provide it information on like how many diagonals below the main diagonal do we have? 1. How many diagonals do we have above the main diagonal? We have 2. And so this is the number of diagonals below the main diagonal, number of diagonals above the main diagonal. That's it. And then you give it a matrix that includes only the diagonals. And then you give it the vector on the right-hand side, right? A, B is equal to B. So you have to supply B. That's what it's solving for, okay? So let's do this on our problem, okay? So let me see. All right. So let's take a look here. What exactly are our values here? So you notice, right? You notice here that we will have a diagonal of just negative R values. And then we will have another diagonal of just negative R values. There'll be a 0 in front there, or like an asterisk and an asterisk at the end there. We'll just put in zeros. And then along the main diagonal, it's a 1 plus 2R along the main diagonal. So our matrix that we are going to be sending to solve IVP is a lot smaller, right? So for example, if we had divided J into, let's say, 50. So let's say if we had a bar, something like this, let's say, right? And we had divided that up, let's say, into, let's say, let me make it a bit smaller, right? So I don't know, how many do I have here? So 0, 1, 2, 3, 4, 5, 6, 7, 8. And let's add more 1 just for fun, 9, right? So you notice here, look at what happens. What happens is that this temperature there and that temperature there, you will assign. You will say, those are my boundary temperatures. So let's say you say that thing is, let's say, I don't know, 30 Celsius. And you say, let's say that thing is, let's say, 70 Celsius. Let's say. So how many unknowns do you have here? Well, the number of unknowns you have is that. That's the number of unknowns you have. 8 minus 1 plus 1, right? So you have 8 unknowns. So you will have 8 unknowns here, right? So you will have, in that case there, you'll have 8 unknowns, right? And then how many discretizations did you have here? You had 10. So nx is equal to 10. You had 10 temperature points, right? 10 nodes. And what happens is that 8 of these things are internal and you need to solve for them. The other 2 are external. Those are boundary conditions that you set them up. And so normally, right, if you were to solve this using a full matrix, you would go something like this. You'll end up with a 8 by 8 matrix there. And you will have a T1 going all the way to T8, right? That's what you would end up with. And so, but instead, what happens is that because we are only going to supply just the bands, right? This thing would be a 3, and this would be a, so we will have 8 elements there. So notice if it's just 8 by 8, we ended up sending in 3 by 8, 24 versus 64. Not too big of a difference. But if this thing was a million, holy moly, right? If this thing was a million, you'll end up with a matrix of 1 times 10 to the 12th power, right? And then in contrast, if we do it this way, we would end up with a million minus 3, 999,997 by 3. That's really massive savings in terms of memory. That's between possible and impossible. I don't think there's a computer on your desktop that can do 10 to the 12th matrix. No, that's hard. You're out of memory, basically. Yeah, so let's do that. Now what happens is we need to create this matrix here. We need to create this matrix. There's many, many ways to do it. You can create this, create that, create this, and then stack them together. You can concatenate, you can reshape. There are so many ways to do it. I was fooling around not yesterday on like the number of ways I could think of doing it. This is the one that I came up with ultimately that seems the simplest, okay? So what we do is let's create first our A matrix and let's make it all 0 at first, and then we'll fill in appropriate values. So NP zeros. So how many do we have? Well, how
Carlos,
many
we can't see Python.
Oh, yeah, thank you so much. Yeah. Okay. So so how many rows do we have? Well, we have 3 rows. And how many columns do we have? It's going to be the number of discretizations minus 2, because you know the temperatures at the 2 ends, right? So it's going to be nx minus 2, right? Okay. So now the next thing is we need to put in the first diagonal, right? So what's the first diagonal going to be? It's going to be A. I need to show both actually in principle. Let me show you. So we have a 0 there, followed by a bunch of negative R values, right? And so what we will do in our Python is we will start at the second position, which is at 1, and all the way to the end, we will assign that to negative R, right? And then for the middle one, well, it's the whole thing. I'm sorry. So this thing is at row 0, right? And for the next one is that for the second row, we will have basically everything, and we will assign that to 1 plus 2R, right? 1 plus 2 times R. And then for the next diagonal, right, it's everything 0 except the very last one. So it's going to be A at 2, and then exclude the last one. Let's leave that to be 0. So minus R, okay? Let's take a look at this. I haven't imported this thing. Import. Okay, so let me show you something that's a bit smaller first. So let's not quite make it 50. So let's make it just 10, for example. I need to put that as a tuple, because you need to give the size as one, as one iterable. That's what it's called, as a one. So as a tuple, this is the x dimension, that's the y dimension. Okay. Let's take a look at our A. Okay. Yeah. So do you see that? So nx, well, nx is the number of elements, number of j elements that we have, right? The first one and the last one are not unknowns. You specified what those are. Those are the temperatures at those 2 ends, right? So you specify those. So you're not solving for those, right? So remember over here, we had 10 temperatures. but the first one and the last one you're specifying. So the number of unknowns you have are just the one in the center. Okay, that's why you need to subtract by 2. Okay. Okay. Yeah, and then now after that we have our B matrix, our B vector, right? So let's take a look at our B vector. So in this case here, what's our B vector like? So a B vector, let's first set them up to be a bunch of zeros first, and then we will modify them as we will then put in the values. Okay. So let's first create our that. So how many unknowns do we have? Because remember, well, I know you can't see the Python. Let me see. Sorry about that. Okay. Let me go here. Okay. And so what happens is how many equations do we have? It's nx minus 2 again, right? So nx minus 2. Okay. Then now let's fill in the blanks. Let's take a look here. Okay. So what do we have here? You notice, right? You notice that each one of this, like every single one of these B values, right, is essentially this, right? Essentially this, right? With the exception, right? With the exception of this, of the very first and of the very last one, because for the very first and for the very last one, right, the temperature at the next time increment at that boundary is actually not unknown. You know what it is. It is the temperature that's specified there. The temperature at n+1, right, at the boundary, the temperature at the boundary is the same as the temperature beforehand at the boundary. It's what you set. That never changes. So you need to add this to the other side for the first and for the last equation for B. So let's do that. Okay. Okay. Can you see this? All right. So let's do it. So the B values are actually all of them. We'll just type it in. So it's going to be R, right? Times the temperature to the left of it, right? So how does that work? How would this work, right? So let's think a bit about this. So notice, it's going to be the temperature to the left of it. So what do we do? Suggestions? So what happens is in Python, you don't use a for loop. You avoid for loops like a plague, basically, right? So basically, although it would work, I'm only commenting to Jared because Jared, is one of the folks who had it in part 3 of exam 2. So what happened is you also avoid actually loops. So what happens is you always use NumPy to vectorize the calculations. You always do that. So what do we do here, right? So you notice, right? This so what happens is that these B values, right? The B values are corresponding to temperature values, right? That are going from what? What are these? What are the indices for those temperature values? Are they T:::? Actually, you cannot see my iPad. They're not T:::, right? What happens is that the temperature values, right? The temperature values that you are solving for there, right, corresponds to does not include the very first. So you start at 1 and you exclude the very last temperature, right? Those things are those temperatures there. Because again, the very first one, T0, and T of just the very last one, those ones are set, right? And so what happens is that this vector here, right, corresponds to temperature values from 1 to -1. So over here, when you are evaluating those set of temperatures, when you say you're going to shift by 1 to the left, right, then shift 1 to the left, right, what would that mean? So if you're going something like this is Tj, this is Tj is referring to that, right? So you have Tj, that is referring to that. That's for any value of j that are in the internal nodes that you are solving for, right? And so if you have Tj minus 1, what does that correspond to? That corresponds to, in Python, that corresponds to T. Well, you're going to go 1 less. So it's 0 to negative 2, right? And likewise, if you want to go Tj plus 1, what are the indices that corresponds to that? Because this j here is representing a value of j for any one of the internal nodes that you're solving for, right? And so this would correspond to T from what? 2 to the end, right? Okay. And so let's enter in these equations. So when it's to enter in those equations, let's take a look. So we have a Tj minus 1, right, at the previous time. So we will have a T at j minus 1. So that means you start at the beginning, right? And at the beginning, and then you end at negative 2, right? So if I don't put in the 0, it means you're starting at the very beginning, right? And then you have the central term. And this one, we have to be careful. It's a plus 1 minus 2r. So it's going to be plus 1 minus 2 times r, right? And then this is just the middle one, right? So it's going to be times T 1 to negative 1, corresponding to all the j values for which this corresponds to. And then you're going to have the rightmost border, right? So plus r times T. And then now, instead of starting at 1, you're going to add 1 and increment it all the way to the very end, okay? So that's our b value. That's our default b value, right? So let me come back here. Okay. So what happens is that's going to be our default b value, this one here, right? But as I kept repeating over and over again, what happens is, remember, when you are solving for the temperature at the leftmost boundary, right? You're going at basically at this temp, when you're solving for T1 there, right? When you're solving for this, right? You cannot solve for this because this is not an unknown. You know what that is. That's the boundary there. That's a temperature at that boundary. You know what that is. And so note this, right? So this one here corresponds to this temperature here. You cannot solve for that because that's not an unknown. You know what that is, right? So this one gets added to the right-hand side of the equation. Okay? That's the temperature at the left boundary. Okay? And so what happens is, to incorporate that knowledge, we have to do the following, right? So we say at b at 0, at the very, for the first equation, right? What is that going to be? That we need to add onto it, right? So we go b0 plus, right? What? Well, the temperature at the right boundary multiplied by r. So it'll be r times T at 0. So that's how we incorporate that in. Oh yeah, that's right. That's a good catch. Thank you so much. Thank you, Jared. Thank you. You saved my butt there. That's a good one. Okay. And then for the last temperature, right? So for the last one, we have to do the same, right? So it's going to be a b at negative 1 plus r. But this time around, which is the one that we know, this one, for the very last line, right? It is the temperature. It's this one here that we know, and that gets added to the other side. Okay, so that's going to be plus r on the other side for the last temperature times T at negative 1. Okay, cool. We are good to go. Let's solve it. All right. So what's the deal here? Let me see. So we need to solve this thing. We need to go solve banded the number of diagonals below and above. So in our case, that would just be a 1. We have 1 diagonal below, 1 diagonal above. So that's going to be a 1 and a 1, and then our matrix A, and then our matrix B, our vector B, and that's it. Cross our fingers, hope it works. Okay? Okay, so let's go. So it's going to be, well, what is it going to be? Well, it's going to be well, let's take a look, right? So rest. Should I call it rest? Let me see. I can't remember. So it's going to be SP solve. Did I import SP solve already? No, I haven't. So let's import that thing, okay? So import, from SciPy linear algebra, import our SPSolve. Okay, hope that makes sense. No, solve banded, I'm sorry. SPSolve is something else, solve banded, okay? Okay. Yeah, I think that's it. So rest is going to be equal to solve banded, right? The number of diagonals below and above. So there's one below, one above, and then our matrix of just the diagonals only, and then our B, our vector. Yoo-hoo, it works. Let's take a look. Rest. How does that look like? That's it. So in fact, actually, let's label that as the temperature, right? So this is actually the temperature at n+1. Did you see that? Right? That is the temperature at n+1. Okay. Yeah, let's just start plotting this thing. Okay, so this thing's getting exciting. So let me cut and paste some stuff here. I don't want to type this again. So let's do this one. Okay, I'll copy that and let's paste it down here. So we go off and plot. So we make a plot of the original temperature profile. Actually, let's make sure that that works first. Okay, let's take a look. Yeah. So what is this? This is our initial temperature profile. Let's make that thing 50. So we got something prettier, okay? So this is at time is equal to 0. That's our temperature profile, right? Notice everything's at 20. And then suddenly at time is equal to 0, the temperature at the leftmost and at the rightmost positions shoot up to 50 and 80, okay? And then now what happens is that we then can determine, so this one here, T, is now 1 second, or in this case, what's our time increment? Our delta T was 0.5. So 0.5 seconds later, this is the new temperature profile. Notice it's no longer all 20s, right? You can see the temperature evolving in, right? And so we will do exactly the same thing that we had earlier here, right? When we were plotting the results, and we will put that here, okay? But now, you notice the following. This expression here, did you see that? That expression there that I highlighted was the previous method that we were using that was giving us a lot of problems, right? Because for r greater than 1/2, that becomes completely unstable, okay? So we are going to replace that, right, with this new approach, which is the Crank-Nicolson method, right, for calculating the temperatures at a later time. Okay, so we will put that into our loop. Okay, but now you notice that to calculate the temperature at a later time, you need to know the temperatures at the previous time. Well, let's take a look here. Notice, thankfully, right, our A matrix, the matrix of coefficient, does not depend on temperature. So that stays the same. We don't have to calculate that repeatedly. But in contrast, you'll notice that our B vector, our vector B, that's on the right-hand side of the AB is equal to B, that one depends on the previous temperature. Well, thankfully it does, because the next temperature has to depend on the previous temperature. So we actually need to have that in here, right? And so that's how we go about stepping forwards in temperature. Okay? And at this point, I think this should work. Cross my fingers, hope it works. Oh, please. What did I do here? Do. Oh, I see. Let's see. For a stick of gum, who caught the mistake? Anybody? Who caught the mistake here? No, we have AB, right? We have A defined here, right? We have A defined here, right? And we also have B defined. So we're all good. So what's our problem? Are you missing zeros? No, we're good. The problem is here. What's wrong with that? What's wrong with that? Let me ask you, what does that do? Wrong shape. Why is it the wrong shape? Why is it a wrong shape? Anybody? No, the temperature that results there is 1D. No. Actually, let me ask you, what does that solve for? What is this going to solve for? So notice what that's going to solve for is this, right? So if you look back at our notes, what does that solve for? Let me see. What does that solve for? It solves for this, right? It's solving for those temperatures, right? Did you see? But what temperatures? What temperatures are we solving for there? Anybody? What is being solved for there? I'll be a bit patient here because if I just keep giving you guys the answer, it's hard to learn that way. Yeah, non-initial temperatures, but in particular, what? Some more detail, some more. Those are what? These temperatures are those are the unknown temperatures, right? Well, the reason you're solving for them is because they are the unknown temperatures, right? So for example, if let's say here we had 10 temperature increments, how many unknowns are there? There are 8. So when you go off and solve for this, how big is that? That's going to be 8. That's the number of temperature unknowns, right? Now, let's take a look at what on earth we did here. So why is this thing wrong? What's wrong with this? Notice up here, what did we do? Did you see that? Our temperature vector, the first and the last elements are the temperatures of the boundary, which we have set to be 50 and 80, right? And so the 50 and the 80, we should not be overlapping them. Especially the 50, you should not be overlapping that 50 with the answer that you obtained for the first temperature unknown, right? And so what we need to do here is that here, well, your solution is only for the temperatures that you don't know. And those are the ones inside on the internal. So that's going to be 1, 2, -1. How's that? Right? Eva, what do you think?
Very riveting.
Darn that vocabulary choice. It's like riveting. My goodness. I shouldn't say I learned a word today, but I'll have to add that to my vocabulary of teaching words. Riveting. Just watch me use that in our next class. It's riveting. There you go. It works. Holy macaroni. It works. Yippee. It works. But now, I will explain that again, Ayula. Alexander, Ayula. No problem. But notice what we're going to do now. Do you notice earlier, right? Do you notice, remember earlier, we could not take time steps of bigger than 0.5. It explodes. This time around, oh, what the heck? Let's make time steps of 5, right? Yeah, let's make time steps of 5. But because we're taking time steps of 5, then now suddenly, we do not have to take 2,000 time steps anymore. We can reduce that down to just 200 time steps, and it really speeds up our calculation. And then we can go off and instead of plotting every 100 time steps in which every time step is small, we can now take bigger time steps, fewer steps, and then of course we can print it more often, right? Not bad. But you notice, of course, we kind of overdid it. You notice it start like, wiggling a bit over there. This time around, that is no longer because of instability. That is because, of course, we are approximating our finite differences, right, over a bigger tempered time difference. And of course, your approximation of that derivative gets worse. The big, if you're saying this is the slope and you're taking it over a big delta t, right? Then of course your derivative becomes bigger in error. So we overdid that, all right? So maybe let's go, I don't know, let's make that, let's say multiplied by 2, let's say 400. And then let's say our delta t is now only 2.5. And then this one is, let's say we print every 20. Something like that. Let's see. Yeah, pretty, right? But now we're able to get away with this with much, much, much fewer time steps. And this speeds up the calculation very significantly. Okay, I will go through this, of course, one more time because, of course, this is your exam, right? So, and I'll give you guys some more hints for the exam so you guys actually have a very good chance of doing it. Okay, let's see. Let's look at the questions. Okay, let me see. Okay, I will explain that one. Andrew, you're a madman. Okay, it's like Mad Max. I'm a madman. I'm a riveter. Okay, where should we start from? Okay, where's a good place to start back? I think let's go back here. It's 12:34. Okay, so what I'd like to do rather is I'd like to explain to you guys how the exam modifications you need to do fit into the framework of what we have. I'd like to spend more time on that. So Alexander, Ayula, there's a part there you wanted me to explain some more, right? Can you be a bit more specific? And I'll explain that and I'll go through this again, but in the context of the exam problem. So I have time for that. Could you be a bit more, can you explain that one more time? So what is that? The part of the dat, is it this part, right? Is it this part here? Yeah, okay. Yeah, so what happens is, so remember, right? So the way we're doing this, right, is we had our bar, right? We had our bar, right? And what happened is we had a bar, we divided that into 10 segments, right? And we say that the temperature at the ends, which we specify there, we have to specify those, right? And we want to say this bar initially is at some temperature, and we suddenly change the temperature on the left side and on the right side, let's say 30 and 70, or now in our case, I think it's 20, I don't know, 50 and 80, I believe, right? And what happens is we want to calculate how these temperatures evolve in time, right? And so notice, right? Notice here is we have, using the Crank-Nicolson finite differencing, implicit finite differencing, we have a vector, we have a matrix of coefficient. These are the temperatures, right, at a later time that we want to solve for, right? Over here, we have a vector that depends on the temperatures that we already know at the current time n. Okay? So what happens is when we go off and solve for these temperatures, notice we're only solving for the unknown temperatures. It's only these guys in the middle that are unknown, that we don't know, right? It's only these ones that we do not know of, okay? So because we do not know of these, right? When we go off and solve this thing out, when we solve these things out, how many unknown temperatures do you not know? It's going to be the number of nodes minus 2. So in this case, it was 10 minus 2. So there's actually only 8 of these, right? But if you look at this, what is our vector for the temperatures? It's actually 10 because it includes the temperatures at the 2 endpoints. But in fact, what we had solved for was only the temperatures, the ones that are unknowns. So when we look at our code, right? When you look at the code here, this solve banded solving the linear system only for the unknown temperatures. So you need to make sure you assign those to the portion of the temperature vector that are actually unknown, which is starting not at 0, but at the second position, which is at index 1, and all the way to just the temperature index just before the last one. Okay, and that's what this thing is doing. Does that make sense? Okay. So now let's take a look at the exam question. Okay, so here's the exam question. This is how it looks like. It looks so pretty, right? Yeah, I know I should have flipped the red and the blue, but I got lazy there. I decided it's okay. You should have gotten from cold to hot, so blue to red. Oh well, let's take a look at this. So well, so it's this thing is a 50-meter long. You're given alpha, you're given delta t, you're given delta x, and you're say discretize it from 0 to 49, right? So notice in this case here, let's take a look at this. Okay, let's take a look at this problem. So this part here, this will be node 0, right? This guy here will be node 49. Okay, of course you can't see that. Okay, so all right. And so what happened is in our problem here, the temperature at 0, you got specified. That thing was specified to be 50 Celsius, I believe. Was it 50? 50 Celsius, right? And what happens is that this side, you say that this side remains perfectly insulated. It's always insulated. Okay? So what happens is we say that this side here, you always have perfect insulation. It's always perfectly insulated. So which means to say what? How would you specify that kind of boundary condition? Notice that in this case here, there's no temperature. Previously, right? Previously, in the previous problem we did, right? At time is equal to 0, and at every succeeding time, you were given what this temperature was. You were told, for example, that was 80 Celsius, or that was 70 Celsius. You were told what this temperature was. But in this current problem, you are not told what that temperature is. You don't know what is that temperature at that site. Instead, what you are told is that after this boundary, it's perfectly insulated, which means to say no heat is leaving. Okay. Now, if you think about it, right? If you think about it, well, what does it mean for this thing to be insulated? What that means is that, so what that thing is saying, to implement that idea of an insulation, right, is you go off and create a temperature at 50, right? I'm not saying that you should actually modify your array. Do not actually create an array that goes to T50, okay? Stop at 49. But what happens is what you want to do is that it's probably, well, let me leave it at that, but I'm telling you, do not include that in your temperature array, okay? So what happens is that this temperature here at this following temperature there, you should always set that to be equal to the temperature here. Because notice, if the temperature here is the same as the temperature there, if they're equal, well, what is the derivative of your temperature? 0. If your derivative of temperature is 0, then what will happen? You will have no heat flow. Okay? So you might be asking, so, well, how do I incorporate this? What does it mean? So what does it mean in the problem statement part 1 when I say something like, write down the set of Kratz-Nichols equation, explaining how you arrive at the finite difference equation for the insulated boundary? What does that mean? Well, let's take a look. So what that means is the following. So you notice, right? Let me copy this again. Let me see if I can get away with copying this. Okay, let me copy it, okay? Copy. Okay, and now let me drag it down. All right, it's dragging. I don't know why it does that. I hope I managed to copy that instead of delete it. Let me see. I hope it's still there. Dang it, I lost it again. Let me undo it. All right. Okay, let me just do it here. All right. So what we're trying to say here is the following, right? You notice, right? When we want to write down, this last equation here, right? Notice the first difference is what? The first difference is that earlier, right? How many unknowns did we have? If we had 50 discretizations, 50 steps, how many unknowns do we have? We had 48. You remember that? Because the last temperature, you know what that is. In this case here, that last temperature, you don't know what that is, right? And so this vector of temperatures, right? Of course, you have to skip the temperature at the leftmost boundary, which you know. But the rightmost boundary temperature, you don't know. You only know that that thing is part of an insulated boundary. So this last temperature, you need to solve for, okay? So now what happens is that when it comes time to solve for that temperature, right, you notice that it requires you to get the temperature one more step to the right. You need the temperature one more step to the right. Well, what did we just say? Well, we just said, right, that the temperature one more step to the right, in order for this node to be an adiabatic node, well, the temperature one more to the right has to be equal to what? Tell me. This has to be equal to what? Has to be equal to this. These two have to be equal. So this temperature, one more to the right, is going to be the temperature at that node when J is corresponds to the insulated end. Likewise, this temperature, one more to the right, must be the same as the temperature Tj when you are at the rightmost boundary, where this is, exactly, right? And so what happens? Well, it changes your coefficient matrix, doesn't it, right? Because if this is the same as that, well, there's a minus r there. You see this minus r? So instead of a plus 2r, you end up with a plus r. And down here, because this and this are the same, instead of a minus 2r, you end up with a minus r, right? And so how does that manifest itself? The way it manifests itself is that down here at this diagonal here, instead of having a 1 plus 2r, what do you have? You're going to end up with a 1 plus r. And then on this side here, when you calculate the last element of that b vector, well, it's no longer going to be like this. It's going to be 1 minus r. So the equation that you use to calculate the value of b, right, on the right side of this equation, the right-hand side of this equation, for the last element J at the insulated boundary, it's going to be different from the ones above. And that's it. It's that simple. Okay? It's really that simple. So it's that simple. So of course, you may want to think through that a bit, okay? So that you could actually explain it, right? And so what do I expect you to do here? Well, what I expect you to do is something like this. So you don't have to go through the stability. You don't have to explain the stability thing. But you want to express this part of it, that the Crank-Nicolson is basically an averaging of the second difference equations, right? Both at the current time and at the later time. This part you can go off and write it down. Then you go off and do the algebra, show it out, right? How you end up eventually to this expression there. So that's your Crank-Nicolson difference, finite differencing. And then what you do next is then you say, hey, at the insulated end, we need to solve for that. For it to be insulated, this temperature, one more to the right, has to be equal to this temperature at that node for the insulated end. Say that for this, say that for that. Emphasize, write out your matrix, emphasizing this difference there and that difference there. That's it. That's part one. Part two, well, modify the code a bit. And then so you get a plot that looks something like that. Okay, and that's it. That's the exam. Okay? You guys can do it. Now, please, if you're gonna be handing it on the last day, please have a reason. Something like, my dad is sick, I have coronavirus, the place I'm living, I have roommates that have coronavirus, or I don't know, two grandparents died because of coronavirus. I'm not making this up. What I'm telling you is the kind of situations your classmates are facing. Okay? And so that's why I'm giving such long deadlines on this, is because you have classmates that are facing some very serious challenges. It's no joke. And so don't abuse it, right? If you don't have a problem, get it done. Okay? Please. All right? You have some classmates facing some extreme challenges, okay? Between this and the other class, there's at least 3 people with coronavirus already, okay? So this is no joke. And that's why I'm being so, I don't want to use the word generous, but it's not being generous. It's just being understanding of what the difficult situation many of you are facing. I don't want to go around asking for excuse letters. That's not classy. If you don't have a problem, get it done, okay? All right, and that's all I have. All right, so this should be a much easier exam than exam 2, I believe. It should be much easier. Okay? Let me see. That's only the last temperature tracer. How much now? I mean, you saw it, right? So what happens is it's so the right hand side, well, you need to also impose that at the boundary, that the temperature afterwards and the temperature at the boundary are the same. And so this R and this 1 minus 2R, becomes the 1 minus R. Yeah. But it's going to be, of course, only for J corresponding to the rightmost boundary. Okay. No, I can't answer that anymore. Sorry. First part, if I had, then we code. Yes, exactly. That's right, Danny. Yeah, that's right. Yeah.